It is the second part of our episode, and again, we are on a journey through the great world of AI and machine learning, and we put it into the context of manufacturing companies. Today, we want to focus on real life implementation and projects, and I'm super happy that again, Justin is on board. Justin, welcome to the Future Proof Operations podcast.
Hi, Benjamin. Pleasure to talk again. Looking forward to it.
Justin, in a nutshell, who are you and what you are doing, especially for those listeners who didn't listen to the first part of the episode?
Yeah, of course. So my name is Justin Hodges. I work in Siemens in their Digital Industries Software segment, specifically concerning our portfolio of simulation and test product. I have a technical role for our product management team concerning AI/ML, and I work on strategy, product, engaging with customers on the technical side, and then thought leadership and marketing and enablement, all rolled up into one role.
Today, we want to deep dive into projects or implementations that you had in the last years. Could you tell us more about the projects that you brought with you?
Sure. So the first one we can start with is a group out of our testing group that does physical measurement. And they've been doing AI for maybe 6 or so years now, early adopter in terms of outside of tech, I would say. And what they're looking at is this use case called anomaly detection, quality assurance, their related themes. And essentially, the project they did and published on, if in case you want to read more, was a
Mhm.
manufacturing or shop floor where there's a lot of people doing different work activities, a lot of equipment, maybe some loading and unloading, and in terms of trucks or equipment and that sort of thing. But really, the key element in there that we're concerning with is that there's these heavy duty engines operating, I think 30 or so on the shop floor. And the goal was to take some sensor data, like maybe microphone measurements, and be able to detect with machine learning methods if all of those equipment, meaning the engines, are operating in a way that's performant and typical and healthy. And if not, then to alert the operating team if there's sort of unusual behavior. That way they can check it out before things get worse. If there's any sort of halt to their operation, or worse, maybe even um, some health concerns or safety risk factors for the people on the floor if there was to be a severe disruption in the machine and it start to break and that sort of thing. So that was really the primary purpose of the machine learning model operating in that environment.
Mhm. So, in a nutshell, we are within the factory, and there are some engines, and we want to find out which of that engines has a failure or which has an anomaly. And probably in the old world, I would need some engineer walking around and finding that failed engine, probably like that. And now you are coming in with your team and you start to use AI and machine learning to detect that engine. So, what did you implement in particular and how did you do it?
Sure. So the and like you said, the legacy way of doing things, maybe somebody would walk around to each of the, you know, motors and then provide some measurement taking to ensure it's operating safely. And maybe periodically they continually do the rounds to make sure they're all safe. Maybe not, and then it's just a risk. But yes, in this
Mhm.
case, what was proposed was and published was actually a framework for tackling these problems. So there is flexibility on the exact models and things like that, but um, it was novel in terms of how to approach this problem. And so one of the key things that was really good about is that it's unsupervised and generic in this way. So in that sense, you don't need a fleet of historical data and going through past annotations. Maybe, I mean, how difficult and alienating would it be if you had to have failure cases present to train the model? That would be very alienating and maybe an expensive thing to replicate or simulate. So in this case, it was opportune to have these blocks. And the core technology there is clustering and hierarchical representations. And so what they actually did was starting with some assumptions, okay, that the majority of the machines in the fleet are operating in a healthy way, and they're more or less under the same operating conditions. So maybe in one shack factory floor versus factories around the world with different operating conditions. And first, the block in this framework of a solution would be to compare machines one to one and make clustering analysis on that small granular level. And then you can even apply industry specific or domain specific business knowledge, whatever you want to call it. Like in this case, maybe you know your failure mechanism is a frequency based thing. As I ramp up the motor at a certain frequency, I have a failure. That's really critical knowledge to be able to put inside a machine learning model. So then you can actually, because it is a flexible generic framework, use time domain data or transform. Like if you wanted to do fast Fourier transforms that are focused on frequency basis. And so you can actually have some implementation opportunities to infuse sort of, you know, a cheat sheet for the machine learning model, what you suspect will be the cause to look out for, right? And essentially, once you have this, all these different clusters, as you make one-to-one machine comparisons, you can make this hierarchical representation almost looking like a random forest or decision tree, right? And then essentially, you again repeat this clustering process on groups of many machines at once and no longer one-to-one. And so essentially, you have characterized what is unhealthy and healthy behavior. Like I said, assuming that the majority of the fleet is healthy. In fact, maybe one of the machines
Mhm.
would be an anomaly in a lot of cases, I would imagine. And then essentially, with that last global sort of clustering, then you can assign anomaly scores. So then every machine has like sort of risk or score associated. And then really that's great because you can visualize that. You can pass it to a dashboard. You can have metrics in a report dumped to the operating team. And essentially, there's some identification of high risk scenarios.
Okay, you walked us through the technology and already a little bit through that process that you applied to make this analysis happen. But I assume it's still super complex for our listeners, and even for me
Yes.
right now, I'm struggling a little bit to understand the the basic process. So how did you start? So when we go two
Sure.
steps back and we have that machinery in that factory, and I ask you now to use your machine learning model to detect the failures, what do I need to actually start or be actually able to start? For example, do the machinery needs to be connected to the internet? Do I need some sensor data to get the data to make that analysis?
Essentially,
Mhm.
you would need some data acquisition system in a traditional experimental sense to acquire all of this data from the different microphones. And in that sense, then you can apply at next basic pre-processing steps for these signals. You know, maybe you don't need all of the data points that could be, you don't need so many data points over time. You could downsample to lower frequencies. That would essentially be your choice. And then essentially you have this data that now looks tabular, and the machine learning models in Python is what you'd start to create based off of that.
So I use the microphones and then I start to record the noise or the sound of the machinery. And how is the mechanism working to bring it then into your machine learning data cloud? I just called it like that, but for me,
Mhm.
it's not very easy to understand how the model understands which engine is actually failing. So does it need your input, for example, or some expert input to detect that?
No. So it's unsupervised in that sense, but as a proof of concept, you could do things in the experimental phase, like, for example, enclosing some of the machines for short time intervals in cages, so that, of course, the
Mhm.
acoustics and the sound coming them would be different. And you could use that as a way to safely impose different conditions to test the model to see if it could pick up on the different behavior, the different sound from the machines, or you could run them at lower RPMs, things like that, or different RPM. And remember, there's a lot of noise, and the microphones are not assigned one to one to a machine per se. You know, they're picking up all the room noise, and so in this test case, that would be like how to evaluate the models. But in a sense, they should be unsupervised and learning themselves without historical
Mhm.
data. So in this case, it's looking at trends, and that's why clustering is such a key aspect there. Now, the second part that I mentioned, kind of like after proving the method works and then imposing some artificial nuances and the operating of some machines and validating that the machine learning model can pick it up, then essentially there'd be formats that you could save your machine learning model from Python out of, like ONNX or these common formats that are not tied to a specific commercial provider. And in that sense, you'd want to take those very small files that are essentially models and deploy them in whatever the IT infrastructure is of the company. So maybe they have very sensitive data. So they have their own cloud that they, use themselves and operate themselves so they keep their data secure. Or maybe they don't have that requirement and then they can have an external cloud provider. And basically, you would want to deploy that model in whatever ecosystem they're using to where the data is collected and uploaded to that cloud. And then essentially, maybe one bucket is where this data is collected. Then you have some sort of AWS application, like maybe Lambda is a popular one, but there's plenty of others
Mhm.
that would essentially have the task of taking the data and assigning it to that block where that model is existing on the cloud, providing some inference, and then pushing it to like an API to the user. So maybe the API, they chose to have, a grid of 10 color blocks, and the operator can just quickly go on a web app or on their phone or whatever sort of portal they're going to use to access their cloud. And it would just show green blocks or red blocks or yellow blocks. And that would be a quick means for, that specific group to say, the model is telling you the anomaly score is high or low or
Mhm.
safe, you know. So it could vary, but really uh, that was the means by which the group acquired the data and performed the project.
Yeah. Super interesting. When you talk about it, it sounds super straightforward. So you have the engines in the factory, you have your microphones, then you put the data in the cloud and it's working. But um, I think there might be some obstacles for you and your team when you implement some technology like that. Which kind of obstacles did you discover doing that project?
Yeah. Well, obviously, it's a clever thing that the group did to come up with this generic framework that's, so flexible. But this was a
Mhm,
collaboration between Siemens, the commercial entity, and university to collaborate and provide all of the data availability and the resources to have access to such a shop floor and run these sort of tests and install the microphones. So not too exciting. I would say it's a very common thing of data availability. Um, I'd say that's probably one of the main obstacles because if this could all be done in a simulation world, then I could sit here at my computer and do all of these things. But physical testing and measurement is a precious resource, even more so than simulation, I
mhm.
would say. So really, I would say it's getting everybody to buy in and invest and do the collaboration to execute this vision. I would say is probably the main obstacle that would preclude people like you and me to just do this from our computer.
When you talk about data availability, is it the data which you recorded in the factory with the microphones, or which data do you mean?
Yeah, I would say that's absolutely critical in terms of making the model. You cannot make that model without the microphone data. And like I said, I mean it's coming from a real floor with operations and things like that. And these electric motors are not cheap, and so I would say that's really the most big obstacle, probably, other than the smarts the team had to come up with this framework and stuff for processing.
When you introduced that project, we talked about the old world and we compared it to your machine learning technology solution. And we said that probably in the old world, you would need some operator walking around finding the failed machinery. But on the other hand side, there might be other solutions as well compared to ML models. For example, I could connect the machine with an Ethernet cable to the factory cloud, and probably the machine can tell me that it's failing. When you talk now about that specific solution, about the model which you used, what are the benefits of that concrete implementation?
Mm. So just to make sure, would you like to know sort of discussion on compared to other approaches possible, or just in general, the return on investment that the company would have if they put in such a project like this in place?
I think both would be interesting. So on the one hand side, of course, what is the the direct benefit of that implementation, and on the other hand side, then comparing it to other solutions. Probably it's much cheaper to just use some of the microphones and put that data into the cloud than equipping all of the machinery with sensors and connecting them to the cloud. I don't know, but I think both steps are relevant.
Yeah. So I would push back a little bit on, the example of not using machine learning and just hooking up the machines to Ethernet cables, and putting it to
Hmm.
the cloud and having the machine directly tell you, whether there's a problem or not. Because, I've installed some of these before or similar type of pumps and blowers for wind tunnels back in grad school. And, you know, they're very, very expensive and heavy and serious equipment in terms of getting them to operate, but yet they still come with very minimal instrumentation for pressure
Hmm.
taps and things like that that you can measure as far as signals. And I think that humans really struggle with looking at time series data and spotting all kinds of local trends that are wrong or large scale trends that take maybe days to accrue. And once you make it more complicated, even beyond just looking at one signal for one motor, right? A bunch of signals at once is now impossible, right? And then you have a lot
Yeah.
of other effects like how to spot an anomaly if, someone operates a motor inside a forklift while all these engines are operating in the environment. So, I would say a huge benefit is just this ability to detect anomalies in healthy behavior. I think machine learning is very, very good at that. And I'd say there are other legacy methods that are possible, but this one seems to be exceedingly helpful in this use case here. And I'd say that's definitely the primary benefit.
Hmm. Interesting. Okay. And if you exclude the comparison to other solutions, what have been the benefit coming directly out of that project, and the benefit for the customer, of course?
Yeah. Well, obviously, in an area where humans are working on a factory floor, then their safety is impossible to quantify in terms of value. It's exceedingly
Mhm.
important above all that, everyone's safe. And I would just feel a lot safer with this in place rather than someone walking around to every machine every 2 hours to make sure everything's looking good. And then, of course, there's opportunity cost and downtime. Even in like power plants with energy equipment to produce electricity, even a day of downtime is millions of dollars lost that they could receive for producing electricity from the different buyers buying their service. And so I think it's absolutely critical to understand the health of your equipment over time, which is really more than just a Boolean is operational or is not, right? Which we as humans kind of see
Mhm.
if it can run versus if it's broken, right? I think that there's a lot more information available to you with these anomaly scores or more generally machine learning models that can do condition monitoring to give you a sense on when it might be a good time to replace equipment preemptively versus after it breaks. Um, so I think it's a very beneficial uh, value add to have this sort of scenario.
Great. It sounds like a great implementation. And to finalize the first project, could you give us a scope of how much resources that project took? Because for me, as a non-expert in that field, it could be like it took you 3 days and the thing was running, or it took you 3 years and the thing was running. So, how much resources are needed? How big have your team?
I don't know exactly. Somewhere between 3 days and 3 years. As I mentioned, I really look after machine learning across our full portfolio of products, which is a huge number of
Yeah.
products. So obviously I'm not, personally contributing and leading every project by any means. And so in this case, it's really our test colleagues, mostly headquartered out of Belgium, I think is where the majority of them are. And they owned and executed this project. I think there were probably three of them on the project, at least in terms of the
Mhm.
final publication that went out externally to summarize the work. But I imagine it was between 3 days and 3 years.
Okay. This is a good estimation. Let's start with that.
Cool.
Let's go to the second project. So,
Mhm.
what did you do in your second project?
So this was a cool one because it was a collaboration amongst the different business units at Siemens within our digital industry software segment. We have factory automation and we have our sim center group, which is again looking after uh, all the different types of engineering simulation and testing data. And so in this case, we took one of our horizontal acting products that could essentially be a place to build models, validate them, analyze their predictions, and use them. And what we did is we hooked that up with our our plant simulation software in the factory automation group. And the point of this one was assembly line scenario planning. Really, the goal is to have faster throughput in the full assembly line. But my understanding is that it's really complicated because even the smallest changes that can be done could have unforeseeably large or small impacts on the final throughput time when you have so many sequential processes. And so in this case, they combined a few different tools. They combined the plant simulation tool, which would generate simulation data for a number of scenarios where you have an assembly line, and then you have different workers and stations at each from start to finish. Now, that was used as a database to generate a lot of data on throughput with respect to all these independent variables. So basically, how long it would take for each station and things like that. Now, all of that data was uploaded to Accelerator Share, which is a cloud and web based application for sharing data like through Team Center or simulation products. And with that, our horizontal product called SimCenter Reduced Order Modeling, which is essentially where you would build machine learning models or other types of surrogate. It was connected to this data and then made these surrogate and replaced that as well onto Siemens Accelerator. That way, anyone working on the floor or designer alike both could connect and then ping this model for an answer on how fast the throughput time would be based on their input on the different configurations for the assembly infrastructure. I kind of shared, there's the product generating the data, the cloud application for people to share data and use the model while they're working, and then this reduced order modeling software itself to build the neural networks, look at their validation and testing, and make sure they're general enough to be used. Is that clear?
Okay, let's go through that step by step. I think this is a good overview to explain the project. I find that project super interesting because it's a common problem in manufacturing that you do the plant simulation or the assembly line simulation. It's a common problem because whenever you start to build a new factory or you reshape an existing factory, you change the production flow, then you need to plan or simulate that assembly line and that production line. And if we compare that with the old world again, I know that there is, on the one hand side, a lot of people, a lot of expert knowledge involved on the one hand side. And it's like a big optimization problem because there are a lot of different input factors within that production line, and you need to put it together that it's seamlessly working at the end. And
Yeah.
what I understood now is that you take all that input factors, you try to simulate it, and then put your model on top, your machine learning model to optimize that. Is that right?
Yeah, pretty much. I would say it could be used for optimization, but I think in this
Mhm.
case, the core use was somebody would want to make changes to material flow, to resource utilization, to logistics. There'd be some change. And in order to sign off or anticipate the change, that would be the final throughput time. Usually, a simulation would be done to get that knowledge. And in this case, we wanted to change that to where a real time prediction from a surrogate, in this case, a neural network model, would be given that condition in terms of the variables, and it would make this real time prediction rather than having to go simulate it. But you could take the model and, like you said, use it in an optimization problem. You would just need another optimization software or algorithm or some optimization framework. And the thing generating the data, which could be a simulation normally, would just be this reduced order model instead. So as long as you tried to use it appropriately and inside bounds that are safe based on how it was trained, then that could also work.
If we compare that to your first project, we talked about the microphones being placed in the factory and you recorded the acoustic signals. With your second project right now, we are just within a simulation, right? Or do we have that scenario within a factory in real life as well?
So you could interchangeably use data that was generated from real scenarios and somebody could annotate scenario one. Here were the different conditions, and here is the throughput time. That would be no problem to interchange or add to the training data set. But in this case, it was used for simulation. And I think it's
Mhm.
much faster to generate the data with simulation than with a real scenario and someone, annotating this by hand and then writing it in a tabular document and uploading it, etc. But they certainly could be.
Mhm.
And then you're right. In this case, in the former, it was time signals and time series sort of analysis. In this case, it's purely tabular data in the sense where you would have, n number of rows that are represent n number of scenarios or samples. It could be n number of simulations. And then in this case, your columns are either independent variables that are, inputs to the machine learning model. And then, of course, the columns that are the result that you want the machine learning model to predict, which in this case would be throughput time. And so, in
Mhm.
a strict speaking way, this is what the data looks like that would be used for training and the machine learning model.
The goal of that implementation has been to get real-time results for that scenario planning. And you already touched some of the technologies that you used, but if you would explain it to somebody who is not an expert in it, which step did you take to implement that, and which technologies did you use to make that successful?
Yeah. So to abstract it to a high level, hopefully I succeed in this description here. But you know, we run simulations for a number of different cases that are possible for your assembly line, right?
Mhm.
Material flow, utilization, logistics, delays at every station. These are the variables that we want to simulate towards the goal of understanding what was the end throughput time. So we do these simulations because they're cheap. We have this software, plant simulation at Siemens to do that. And then we make a model that can make this correlation to understand the relationship of these inputs and outputs. And we put that model in the hand of the people designing it and the people operating on the assembly line. And then rather than having to pause their work, go run these simulations, and then come back and understand what the changes would do, hopefully they have a web application or some easy way to just type in numbers, hit enter, and the model will be there on the cloud, taking in their result, taking in their data, and just telling them how long it would take. So maybe someone's walking
Mhm.
on the floor with a tablet and they enter 5 numbers and hit calculate, and that's all that it does to get this information back to them, rather than maybe alerting a designer that has all the simulation tools in front of them. They run the case in the simulation, and then they get back to them and tell them the answer. So you can see this information input is, you know, more rapid. They have this model that's on demand.
This is already a great segue to the benefits of the implementation. So as I understand it, you have faster results and probably more accurate results. Is that right? Or do you see other benefits?
That's by far the front runner. But there's also a
Mhm.
paradigm shift in what this allows you to do. Going back to episode one, where we talked about this metaphor. You said something to the effect of, if machine learning apps and capabilities become integrated into the tools people use at work, what they do actually now is expanded. They can do more. And so in this
Yeah.
case, the person operating on the line can now get access to information they previously couldn't via these machine learning apps. So if you think about the possibilities that gives you as a company, the paradigm shift, the person designing the equipment and the situations and the assembly lines versus the person maintaining them are now less air gapped. They're more able to do the other person's sort of work, which I guess is a weird way to say it, but they start to have more competencies from the other person, which is very, very valuable for both people. And so I would say that's also a huge benefit.
I really like that. It's fascinating because I think it really changed the roles of the workforce in the factory in a way that it's empowering them. And I really like that.
Yeah.
When you talk about that implementation, I assume here again, there might be some obstacles as well.
Yeah. Um, this one I think is fairly straightforward though. And I think that's a good opportunity for us to talk about the state of areas and industries like ours in computer data engineering and engineering simulation. We don't need the latest, most advanced, most expensive, high parameter count machine learning model to benefit, right? We just need
Mhm.
investment agreement at an organizational level to build up these teams and competencies and then place trust that they will pay us back and be beneficial in the long run. In this case, the power of how this model can work and fit and understand these correlations is just a neural network, right? I mean, those have been around for a long time
Mhm.
now. It's not like they say you have to use GPT-4, right? That just came out recently. And so I think in this case, it just takes time for the users to become educated from
Mhm.
a bottom up and top down level organizationally so that people can make these investments in teams to create these capabilities. And I don't think there are that many technological issues. This was actually a project that our team did in like 3 days for an event where we wanted to rapidly show this proof of concept and create it. So I think it was 5 people in 3 days, um, 3 working days. So it's not a huge effort to create this, and nobody had to write code from scratch. I mean, this was commercial capabilities. So in this case, I'd say not too many obstacles, but to be fair, right? Machine learning is always a trade off of accuracy at the cost of overfitting and generality, right? How widespread can I use the model and still maintain accuracy? It's always a trade off between those two. So in this case, let's say you really bought into this proof of concept we talked about in this project, and you wanted to disseminate this across all your assembly lines. Well, that's a huge space. That's a very large number of permutations on everything that's possible. Now challenges would be things like which scenarios do I need to generate simulation data for so that I can use the model in this widespread area? And how do I know when not to use the model because the results would be cockamamie because they weren't trained in that space? That is
Mhm.
that is a challenge at that point. And that's where you do need some data science knowledge for analysis and sampling and understanding where you can't use the machine learning model. So that would for sure be an obstacle if you took this project to the next level in your factory or your company.
Great. Super interesting. Thanks for sharing your experience with the two projects. Unfortunately, we are already coming to the end of this episode. And in the end, I would like to ask you one question. I assume for most of the listeners that AI and machine learning topic is still a very complex one and probably something where they find it hard to keep up with. Yeah. And let's assume I'm a CIO of a manufacturing company, 4,000 employees, and I do not want to fall behind. I want to start to work with AI, for example. I want to do the first step with machine learning. What do I need to be able to implement that? Do I need to build my own AI team, or is it just calling your team, and you will help me to do that? What you would d- what would you suggest?
So that's a good question. And I'd say the trend that I'm seeing from even major, extremely large companies, um, is some have tended to create these models themselves. The really
Mhm.
relatable example is ChatGPT, right? So a lot of companies have taken the initiative to make a large language model team and develop, you know, use cases and technologies surrounding and using large language models themselves. But I would say a more popular trend that I'm seeing is companies are now making that a requirement in the vendors that they buy from for their products. They would now place the expectation
Okay.
on those companies to include that in their offering so that they do not have to do this big upfront investment time and very difficult thing of hiring a bunch of people that know this thing and stringing together a strategy at the company. So I would say the latter is a common and easy sort of way to start, and I would just put the expectation on your vendors to provide this included in their products, and then that takes a bit of the headache away from you and more of it onto them, which is what you're paying for.
Thanks for that advice. Justin, it was a pleasure to have you on the show. I learned a lot, and I'm looking forward to have a new episode probably next year where we can dive more into that topic. Thanks a lot.
Yeah, my pleasure. It's always a nice conversation we have. So thanks for that.